Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding dimensional analysis and dimensional homogeneity. So dimensional analysis, actually it is a method of dimensions. You can say this is a method of dimensions. We can write here, it is a method of dimensions. Or else we can define in such a way that it is a mathematical tool. We can say it is a mathematical tool which is used, or it can be used. It is a mathematical tool which can be used for research purpose, or can be used for research work. In the research work, in the sense, it can be used for the designing or for conducting some kind of test. So, okay, it can be used here. Now, actually, as I told you that this method is, this is a method of dimensions. First, we need to know what is dimensions and what are the types of dimensions are there. Actually, in the dimensions, we are having first one, 3 fixed quantities are there. 3 fixed quantities or fixed dimensions are there, we can say. 3 fixed dimensions are there, or we can say that is also called as fundamental dimensions. That is also called as fundamental quantities or fundamental dimensions. What are the 3 items are there? First one is mass, which is defined M. Next is length, that is L. And next one is time, this is T. And remaining dimensions are derived from the fundamental dimensions, that is called secondary. That is called secondary, or we can say derived dimensions. Because why it is called secondary or derived dimensions? Because all the dimensions, remaining dimensions, are derived from the fundamental one. That's why it is called secondary dimensions or derived dimensions. So what are the examples can be taken on this secondary and derived? Let me take an example of, suppose, very simple, area. So area, actually we know that meter into length into length. So that means we can write length into length. So that is L square, that is L2. So this is nothing but the dimensions here. Similarly, let me consider some volume. Okay, some volume. So volume is nothing but L into L, length into height into width. So we can say LQ. So that is its dimension. Okay. Similarly, we can move to the next one, like some difficult one. Let's go for, suppose, velocity of a fluid. So velocity, actually it is defined as the fluid distance traveled by the distance with respect to time. So distance means we can say some length, and time with respect to means t. So this one we can write, the dimension is L t to the power minus 1, that means t inverse, and always need to be marked with respect to some square bracket. So this is about velocity. Similarly, density of a fluid, suppose. So these are some parameters I'm talking. So density is denoted by rho, and which is known as mass per volume. This is mass per volume. So mass equal to, here already mass M is there. So now we can consider M, and volume already we have written here LQ. So now we can write M L minus 3 inverse inside a square bracket. So similarly, we can write some other things like acceleration. So acceleration is nothing but the velocity with respect to time. Okay, you can write here small a, or you can omit anything. So now this is velocity with respect to time. So velocity already you have derived. So velocity is nothing but L t to the power minus 1. So divided by time t. So now we can write this acceleration is square bracket start L t to the power minus 2. This is about the acceleration. And some more things we can also derive, like discharge, suppose. Discharge of a fluid or rate of fluid. So we know that discharge equal to, let's write here, let's write discharge equal to we can mark it Q, and this is known as the volume of water with respect to time. The volume of water, the rate of flow, that is actually. So discharge you can write. So how we can define, or how we can derive this discharge part? Area into velocity. Area into velocity. Continuity equation we have studied, that is A1 V1 equal to A2 V2. So here we can write area into velocity. Area, how much? L to the power 2 we have derived. Now velocity, this is L T to the power minus 1. So both you combine, what will get? L to the power 3 LQ minus T to the power minus 1. So this is about the dimension of a discharge. Similarly, many things we can derive from this. So all are coming under secondary because it is derived from the fixed quantity or fundamental quantity. So force F. So here also we can write force equal to, we know that, mass into acceleration. So mass already, m is there, acceleration already have derived, that is L, L T to the power minus 2. So if you combine, what will get here? We'll combine m L T to the power minus 2. So this is all about the secondary unit or derived units. Similarly, we can calculate many more, like viscosity, dynamic viscosity or kinematic viscosity, specific weight. So many more are there to define. Now the concept is why we required this dimensional analysis in the fluid mechanics actually. So this is very much important to do some kind of analysis part, as I told you, and some benefits also there. What are the benefits can be called? Like we can simplify, or you can simplify some complex problems. Some complex problems can be simplified. And apart from that also, we can design some models. By this analysis, we can design some model design can be done. And if you do some analysis initially, then it will be helpful to do the experiment. And so that we can get, like we can increase the experimental analysis or efficiency. So you can say experimental analysis efficiency can be increased. Efficiency enhancement, you can do that. Okay, these are some basic things as I told you. Now when the suppose fluid is flowing maybe within a pipe or in an open channel, so there what is the velocity of a fluid? Okay, what is the velocity of a fluid, and what is the length of the pipe suppose, or what is the diameter of the pipe? Okay, what is the density of the fluid? So all these are parameters related to the fluids, correct? And these are the length and diameters are there. Apart from the viscosity will be there. So by considering all these parameters, we can do dimensional analysis. That's why it is more important. And the next part is, as I told, this is dimensional homogeneity. So dimensional homogeneity, let do it in this page itself. So dimensional homogeneity is also very simple. Like this is the concept actually. Yeah, the dimensions of each term actually. Here, let me write dimensions of each term. Suppose one equation taken, that should be equal in the both side. In equation, both term will be there, right hand side and left hand side will be there. Okay, so here dimensional homogeneity means both side equation, the dimensions should be same. Obviously it will same, but let have a test on this. So for the dimensional homogeneity, let me consider an equation related to Petri tube. Okay, so we have studied in the Petri tube time that velocity of fluid, how to calculate it. So we got the equation there, V equal to root over of 2gh. Now here, if you see, this V is left hand side and this is right hand side. So let me mark here. This is here. We can mark. This is left hand side and this is right hand side. Now we need to verify both side equation dimensions. So velocity already we have calculated. Dimensions we have calculated already. That is L T to the power minus 1. Now the right hand side we need to derive. That is root over of 2gh. So we can write root over of 2 value is constant, not required for this. G equal to, we know that gravity. So G unit you can write dimensions L by T square, L by T square, and meter per second square you can call it. And H is head, H equal to head, or that is nothing but the distance. So that is also L. So here if you multiply this one, we can get L square by T square root over. Now if you do the root over part here, then what will get here? You can get L by T. And here if you see this, I've just removed the root over part here, and so I got this one. Now you can write this one. You can write L T, this is minus 1. Okay. Now if you see this equation and this equation, this is the left side equation, this is the right side equation. Now we can say the dimension of, left hand side equal to dimension of right hand side. Okay. So this is called actually dimensional homogeneity. Both side dimensions should be same. It is quite simple and known to everyone, but this is the thing. Okay. I hope you understand what we have discussed in this lecture, dimension analysis and dimension homogeneity. Still, if you are having any kind of doubt regarding this, you can give a comment on the comment box. Thank you all.